So today we'll discuss about the state equation, state table and state diagram. So we'll understand what do you mean by state equation and what is a state table, state diagram. So to analyze any sequential circuit, we have to go through some very specific kind of procedure so that we can understand the characteristics of an sequential circuit. That's why these three things becomes an important technique to analyze any sequential circuits. We know that in any sequential circuit, the output is dependent on the present state. So the present state, which is defined by the data that is stored by the D flip-flops or maybe resistors. So it is dependent on the ones and zeros that the sequential circuit is storing in the storing element like the D flip-flop, and also on the present input. So the output is dependent on the present state as well as on the present input. So if this is my sequential circuit, so I have some states here. Let's call it as the present state. The output is dependent on the present input as well as the present state of the sequential circuit. So here we'll be basically trying to understand, trying to analyze how does the sequential circuit works, or how do we analyze it, because it's very difficult, right, to know what will be the next output. Suppose if I want to predict what is the next output, and if I know the present state and the present input, how do we characterize the complete sequential circuit? So we have these three methods as we have discussed. One is the state equation, the other is the state table, and we have the state diagram. So now let's try to understand what does this state equation means. So let's consider these two known scenario. We know the operations of a D flip-flop, and we know the operations of an edge triggered JK flip-flop. So we know that for the input for a D flip-flop we have this D, Q and Q bar, and suppose the input is D and the output we are representing with this Q. So the state, how do we represent the operations of these equations? Of course I have this clock, and so the expression for this state equation for this, how it is written is Q t plus 1 equal to dt. So what it means is that in the next rising edge of the clock, Qt plus 1, the next state will be nothing but will be equal to dt, or the current state. So the t plus 1 represents the next state and t represents the present state. So this is how the state equation is used to express a sequential circuit. Of course, the sequential circuit can have the flip-flops and with combinational blocks also, but here it is like simple D flip-flops, no combinational blocks, like that. So similarly, if you try to write for these JK flip-flop, these happens to be, suppose my input is here J key, and we have this Q, and of course this is represented by this one. Let's represent it here. I have represented as Q dash, or with this this I'll be using this notation. So either you can use this one or this one. So in this case we need to write the expression of this Qt plus 1, which is the next state of the output. So here the inputs are J and K and the outputs and Q bar. So or Q complement. So here I'll be writing this Qt plus 1 is nothing but it's Jt, present state of my J, and Q complement or it is the present state of the K and Q. Present state of the K complement and Q. So this is how this is the basic operation of the JK flip-flop, which you had studied earlier. So of course, if you try to draw the truth table, you will see that this is matching, this equation is matching. So if you make JT KT here, QT plus 1 is nothing but the, if it is 0 0, we have we know in this case it is so if this is 0 means J and K means this is 0, of course the K is 1, so it will be nothing but the QT, okay. And of course if it is 0 1, so if it is 0 1, so my this J is 1 and K is of course 0. So K complement is of course 0 and J is also 0. So no matter what is the value of Q T or Q complement T, it is simply 0. And if it is 1 0, so this is which means that this is 1 and this is also this is also 1. So it's basically what it means is Q complement or Q, which means that A or A complement, which means it is something like A or A complement, so which we know is always 1, right? And similarly if I have 1 1, so this is 0 and this is 1, so I have my Q dash T. So this is what we had discussed about this JK kind of flip-flop. It has this kind of equation. So the next state is nothing but the if it is 0 0, it is same as the present state. If it is 0 1, it will be reset, and if it is 1 0, it will be set, and if it is 1 1, it is complementing the current Q. So now although we can use this kind of T to represent the present state, but to save to save the space and to simplify it, we can even just write this without this T. So how it is written is Q T plus 1. So we need to maintain, we cannot just write Q equal to D, then it will be difficult to identify what's the next stage. So the output can be written as Qt plus 1 and the D will be written as simply D by just dropping this T. So similarly here also we can write Qt plus 1. So this means that the next state is nothing but J Q complement or K complement Q. So so this is how we have dropped this T. So which it means here that this is the present state and the next future state is dependent on this equation. Okay. So now let's consider an example of this sequential circuit. Let's consider this sequential circuit as an example and try to find out the state equation of this circuit. So of course I have this D flip-flop, two D flip-flops are there, there are different gates, I have not yet connected them, so I will be now connecting them, and we'll try to write the state equation for this circuit. Okay, so let's go step by step. so this is my input, x is my input, and this input will be connected to directly to the one input of this AND gate, and of course this input is also connected to the one of the input of the next AND gate. It has this output which is A and A complement, so the other output is B and B complement. Because I have two D flip-flops, so I can have two different states. So this can have 0 and 1, this can have 0 and 1. So basically here we can have 2 into 2, we have 4 different states of this complete sequential circuit. We'll come to this point with more details a little later. So now I have this input. In this example, I have this input of this AND gate connected to this B, and this is A complement connected here. So again this X is again connected here, as an input to X, X is again connected to, as an input to it is another AND gate. Okay, so of course this input to this this gate AND gate is from this output of this A. And after this basically this is my final output Y, and this has this has two inputs. So one is from this B, and the other is this A. And the other input of this NOT is from X, Okay, so this is my complete sequential circuit, and I'll be trying to analyze it using the state equation. So now if we just write the intermediate output, suppose this is my node A, so here it is nothing but this A and X. Of course I'm not using the notation T here, so for time being I'm just omitting here. So I'm just trying to figure out what are the input to this D flip-flop. So here it is the input to this AND is B, so B and X. Here also it is like A complement is coming here, So A complement and then x. So now let's try to see here, this is nothing but this A x or B x. So now I can easily write my state equation. So the state equation is, we can easily identify that it's not it's just the output of these it's just the how you're writing the output of this D flip-flop in terms of its input. So similarly the output of this other D flip-flop in terms of its input. Of course I have a clock here, so which I have not shown here. So it's this clock. This is my clock. So these D flip-flops are operating at the positive edge triggers of this clock. So let's start writing the my state equations. So I can write this A t plus 1 . This is AX plus BX. So it is basically AT, XT, BT, XT. Okay, so this is the state equation of my this AT plus 1. Okay, so similarly we can write this BT plus 1 in terms of A dash and X, which is nothing but so it is A complement, so A complement X T, right? So now this y is basically it is dependent directly on the, you know, I can say that it's dependent on the present x and also this the present state of A and B. So whatever is currently at this present state, so the y will be the output y will is just dependent on the present state of this A and B. So and also the x. So the it is, if you see it, it is y t is nothing but this. Here I have my A or B, and this is x complement, right? X complement. So y is nothing but y t is A or B and x complement. So now, as I have mentioned earlier, that we can omit this t here in the right hand side just for the simplicity of and if it is t plus 1, we will be omitting the, you know, we'll keeping it as it is, but if it is in this case because it's this present state yt, so we'll be omitting from this yt also. So the simplified simplified expression or the state equation for this circuit will be, so if there is no this t is mentioned here, it means that it is the present state. Okay, so this is how we try to identify the state equations of an sequential circuit. So the next thing that we will try to see is the state table. So how can I, of course now I have written these state equations, but then can I write some kind of a truth table for this? so that it becomes easier for me to analyze. So just like in the combinational logic we have written a truth table, so can I form some kind of truth table? So because it has these three outputs here, and of course not three outputs, A and B is the internal state and Y is the output. So we have only, basically we have, in this case we have only two outputs, or sorry, we have only one output and one input, and A and B are the internal state of the system. So if you see here, X is the input here and Y is the output, and A and B are the intermediate nodes, which are the intermediate state because they are the outputs of the D flip-flops. So, so this is how a state table is written. So I have my this present state and I have this input. This is my input and this is the next state and this is the output. So, so what I can have is because I can have in the present state, because I have two D flip-flops, so I can have 4 states, and the inputs I can have total 2 states, so either it can be 0 or 1. So these 3 combinations will have total 8 states because 2 into 2 into 2, so it is total 8 states. So I can just write down all the possible combinations because it's 2 power 3. So I have 8 states, so it's 0 0 0 0 0 1 0 1 0 0 1 1, just like we write in like in a truth table. So you can write all the 8 combinations. Now one by one, let's see what will be the next state based on these equations. Like what is the next state of A and B based on this equation, and what will be the output. So I know this A and B of the present state, and I know the input, so output will be dependent on the present state and the input. So if I try to populate this truth table, so in this case it is 0 0 0. So if all of them are 0, in this case A will definitely be 0 here. Let's use this. And B, in this case B also will be 0 definitely because X is 0. So if X is 0 and of course even though is A complement is 1, but it will be 0. So what about Y? Because A and B are both 0, A or B is 0, so it will be definitely be 0 here, right? So now let's see next. The next is in this case it is 0 0 and 1, right? So definitely my A will be 0 because both A and B is 0. So a next state of it is 0. Now in this case A is 0, so A complement is 1 and X is 1. So it is 1 or 1 and 1. So B will be 1 in this case. Okay. So now because A and B are both 0, so Y also will be 0, right? Now if we go to the next one, so in this case it is 0 1 0. So the X, because the X is 0, so definitely the A of the next state will be 0 because X is 0 here, X is 0 here, so it will be 0 here, and the B also will be 0 because X is 0 here, so definitely it will be 0, and Y in this case, because it's 0 1 and X complement, so 0 1 and X complement, so this is 0 1 and X complement is 1, so it is 1, right? So the next one is 0 1 and 1. So now if you see here for the A, so of course this is 0 and 1 and this is 1 and 1. So this means it will be B will be 1 and A will be 0. Sorry. Um, so okay, sorry, I take it back. So this is this means this in case A is 1, right, and B in this case it is A is 0 and this is 1, so this is also is 1. Okay, now what about the Y? Y is X complement is definitely 0, so it is 0 because X complement is 0, so it is 0. So whenever this X is 0, that means the Y will definitely be 0. Sorry, when X is 1, Y will definitely be 0 because X complement is 0. So in case of the 1 0 0, if we again try to analyze it, you can try to do analyze yourself. So you will see that it is 0 0 and then Y is 1. And if you go for, so I'll quickly write down all these all the remaining ones. You can just try to do analysis yourself. Okay, so I have written down all the next state of A and B and also the output of Y. Okay, so this is how we get the state table. So the state table has the information of the present state and the input, current input, and the next state. So we can see here, if you have if the number of inputs, this table, the rows of the table is dependent on the number of the states, right? Number of the states or the flip-flops it has, and the number of inputs. So if I have, suppose, m states and the number of input is n inputs, so the number of rows for this kind of state table will be 2 power n plus m, because we want to find out all the possible combinations of the input and the present state. So total we have 2 power n plus m rows. Okay, so this is how we can find out the state table. Now there is another way of representing this state table in a little different way, but it is the same thing. So we can represent it in a little different way. So I can write the present state in this form. I have this basically these two deflectors are there, so 4 possible combinations 0 0 0 1 1 0 1 1. So now we can write the next state based on the inputs. So x equal to 0, x equal to 1. So basically we are trying to split the next state of A and B whenever x is 0, and then the other is whenever x is 1. So so what I can write is, whenever try to write out down for all this whenever it is 0 0 and when this x is 0, so you can just write down all the next state of A and B, and whenever the next is 1, again you can try again write down the next state of A and B, and of course similarly for the output Y. So let's try to do that. So whenever the x is 0 and the A and B is 0 0, so we know that it is 0 0, x is 0, so the next state will be 0 0. So I just need to write down this one, so which is 0 0. So the next whenever the x is 0, the next one, which is this one, basically 0 1, so this is the one, so we can write down it as, again it is also 0 0. So whenever the next x is 0, input x is 0, and when it is 1 0, again it is also 0 0. So either we can use this equation to fill this table in this form, or we can again from this also we can find out but if you are directly trying to make this table, we can directly use these equations also. So for example, in this case it is a and b is 1 1 and x is 0, so we know that this state will always be 0 whenever the x is 0, so we can just directly write it as 0 0. So because this a also will be this b also will be 0 whenever the x is 0, and b and a also will, next state of the a also will be 0 whenever x is 0. Now if in case of x is 1, so definitely you can see here if both of them a and b is 0, definitely this a will be 0, but if one of them is 1, we can clearly see that x is 1. So if either a or b is 1, then we can directly say that it is 1 1 1, right. Similarly, in this case, when x is 1, right, when a is 0, we can say that b is equal, next state of b is 1. So and a is 0 in this two case, and because I can so easily write this is 1 1, and however for these two cases a complement is 0, so I can simply write it as 0 0. So similarly for the y, so whenever x is 1, so whenever x is 0 in this case, right, x is 0, so then this will always be 1, so it is nothing but simple a or b, right. So whenever x is 0, it is not, the y is nothing but a or b. So what I have is 1 1 0 1 1 1. So now the next is whenever x is 1, that means this is 0. So no matter what my a and b is, all my output for y will be 0. Okay. So this is how this is another way of using the writing the state table. Of course, in this case, if you see that if the number of inputs is large, if I have 3 or 4 inputs, representing this form may be difficult because my number of columns will be expanding. So if I have only one variable, this number of columns, in this case it is 1 2 3 4, but if I would have two if I would have two inputs, then it would have been 4 into 2, total 8 columns, so it becomes difficult. Similarly for the output also. So so depending upon what is the number of inputs and output, we have to either go for this way of representation or this way of representing the state table. So the next thing that we want to discuss after discussing the state equation and the state table is the next thing that we want to discuss is the state diagram. So what is this state diagram? So yes, it is okay to represent in a table format, but to understand the operating of a sequential system, it is much easier if you go for a diagram representation. So how do we do that? So in the state diagram representation, we'll try to identify the number of states a system has, and then based on that we'll try to draw circles. So in this case, in this state, we have basically total 4 states, right? We have total 4 states in this case. So we will be drawing 4 different circles. So because we are having four states, so we'll be drawing 4 circles. So 1 2, 3, 4. So these 4 different circles represent 4 different states. So now I will try to enter each of these name or each of these state in the 4 different circles: 0, 0, 0, 1, 1, 0, 1, 1. So 0, 0, 0, 1, 1, 0, and 1, 1. So this is how we start drawing the state diagram. So now here we have 4 different states. So here basically we want to know what is the relation between each state depending upon my present input. So if suppose if I am in this state 0, 0, I want to know when it will go to either 0, 1, 1, 0 or 1, 1. So I want to know this transition, the possible transition. So we know that the transition will happen only when there is some input, change in input. Okay. So if we see here, so if my present state is or if my present state is 0, 0, right? Let's focus on this row. So if my present state is 0, 0 and if my input is x equal to 0, then my next state will be 0, 0 and the corresponding output also will be 0. So if my input is 0 and the present state is 0, 0, my next state will be 0, 0 and the output will be 0. So I want to represent this in the state diagram. So this is represented by this arrow, right? So this arrow is telling that, and of course this 0 and slash 0. So this 0, this represent the present input and this 0 represents this output. So basically what it is telling that if my present state is 0, 0 and if my input is 0, then the next state will be the same one. That's why it is so this kind of circle arrow mark, right? And the output for this will be 0. So this is how this is represented. So the next one that we'll try to see how do we represent this this next one. So basically not this one, we want to go in the same one. So we want to represent it now this one. So my present state is okay 0, 0 and whenever the x is 1, you'll see that will be the next state will be 0, 1 and in this case the output will be also 0. So the next state is 0, 1 whenever the input x is 1 and the output will be 0. So this is represented by like this. So my current state is 0, 0 and the next state it is going is 0, 1, 0, 1, next state it is going is 0, 1 and the output is output for x equal to 1 is 0. So my input for the current whenever I am in this state 0, 0 and whenever my input is 1, by next state will be 0, 1 and the output corresponding output is 0. So this is how it is represented by this arrow mark. Okay. So now we have completed the transition of 0, 0 to other one whenever there is input x equal to 0 or x equal to 1. So basically we have completed this first row, or you can use this table also to find out the state diagram same. So basically in this case we have completed this 2 row. So now if we see this third row, right? So my present state is 0 1 and present state is 0 1. So basically I am focusing here now 0 1 and my present input is 0, okay, present input is 0. Then my next state will be 0 0, okay, it's going back to 0 0 and my output will be 1. So my present state is this 0 1 and the next state will be 0 0. So the next state will be 0 0 and of course I have to, my input in this case was 0 and output will be 1. So my input in this case was 0 and the output is 1. So it's very easy to represent the things in state diagram. So I have considered now the input of 0. Now next is I need to consider when the input is 1. Okay, so in my current state is 0 1. So this is my current state 0 1 and my present input is x equal to 1. Okay, x equal to 1. So the next state it will be going is 1 1. So I can just simply draw this diagram, right? So whenever the x input is 1, my next state will from this state it will be going to this 1 1. From 0 1 it will be going to 1 1. But now what is the output now? Then output is 0. So then I can write 1 slash 0. So I can write as 1 slash 0. So the from this 0 1 it is going to 1 1 whenever the input is 1 and in this case the output is 0. So similarly I can go ahead and find out for this. The next thing is for 1 0. So I have completed for 0 0 and 0 1. So now I will be doing the same thing with 1 0. So in this case 1 0, if the input is 0, the next state will be 0 0. So we can just draw a arrow mark from 1 0 to 0 0, something like this. Yeah. So now what is the output in this case? The output in this case is 1. So if the input is 0, the output is 1. So I can just simply write it as 0 1. So input is 1 and output is so input is 0 and output is 1 and it is going from 1 0 to 0 0. So the next thing that we'll see is from 1 0, if the input is 1, my output is 1 0. So I can it is going from when the input is 1, it is going from 1 0 to 1 0. So it is coming back in the same state. So basically then I can again draw this kind of arrow where it is indicating that it is staying in the same state whenever the input is 1. And what is the output corresponding to this? Output corresponding to this is 0. So whenever I'm in 1 0 state and whenever the input is 1, again the output is 0 and it is staying in the same state. So the next is we'll go for the state of 1 1. So whenever it is 1 1 and the input is 0, the next state it is going is to 0 0. So the next state it is going is to here to 0 0 and in this case the input was 0 and the output is 1. So again I can write this and the input is 0 and the output is 1. So finally we have this last one remaining wherever the present state is 1 1 and the input is 1 and the next state will be 1 0. So the next state will be 1 0 and in this case the output we have is 0. So what we have is here is 1 0. Okay, so this is how this is the complete state diagram. So this state diagram is very useful, or it's like a pictorial representation of the complete sequential circuit. So from here we can know from which state it is going to which state, and we can understand like that. So from this we can very nicely analyze, pictorially analyze, because for a human being to understand this kind of truth table maybe sometimes even difficult. To understand this kind of this kind of equations is even more difficult. So easier than this equation, state equation is the state table, but more easier than the state table, the easier one is to understand the state diagram. So the generally process followed to analyze any any sequential circuit, what we follow is we initially we start with the state equations. Based on seeing the system, we try to write down the state equations. Then we go to the state table, and finally after that we try to draw the state diagram. Okay.